Welcome back. In this video, we're going to look at examples of representing a function as a power series by taking the derivative or integral of a power series. Let's get to it. All right, so here's our first example. We want to find a power series for f of x is equal to arctangent of x centered at 0, and then we want to determine the interval of convergence for that power series. All right, so this function that we're given, arctangent of x, it doesn't look like a function that we can easily express as a power series, right? Typically, when we represent functions as power series, that function is in a form similar to the sum of a geometric series, right? Remember that a geometric series is a sum from n equals 0 to infinity of some constant a times a common ratio r to the power of n. And that geometric series converges when the absolute value of r is less than 1. And when it converges, it is equal to a sum that is calculated by taking a divided by 1 minus r. Okay, so typically we look for a function that is similar to this form of the sum of a geometric series in order to express that function as a power series, or more specifically, a geometric power series. Okay, and the most basic case of that is if we had the sum from n equals 0 to infinity of x to the power of n. The sum of that power series would be 1 divided by 1 minus x. All right, 1 is our value of a, and x is our value of r. Okay, so typically we look for functions that are similar to this form so that we can manipulate them to be in the form of a sum of a geometric series. That way we can represent them as a power series. But in this case, arctangent of x looks nothing like 1 divided by 1 minus x, right? And so what we can do is look at either the integral or the derivative of our function, and if either of those functions are similar to this form, then we can represent that function as a power series and then integrate or take the derivative of that power series to get back to the function that we want to represent, right? So here's what I mean by that. What do we know about the integral or derivative of f of x here? Well, we don't know a nice rule for integrating the arctangent function itself, right? We know how to integrate into an arctangent function, but the integral of arctangent itself isn't a rule that we know, but we do know the derivative of arctangent of x, right? Remember that the derivative, f prime of x, of arctangent of x is 1 divided by 1 plus x squared. And so notice that this derivative of arctangent of x is similar to the form of the sum of a geometric series. We have a constant divided by 1 plus some common ratio r. All right, now we would want that plus to be a minus, but other than that, this is pretty close to the form of the sum of a geometric series. And so what we can do is represent this derivative as a power series and then integrate that power series to get a power series that represents the original function. Right? If we integrate a derivative, we get back the original function. Okay, so that's kind of the idea of what we're going to do here. In this example, the derivative of our function is what we're going to represent as a power series first. And in our second example, we're going to see a function whose integral can be rewritten as a power series. All right, but let's not get too far ahead of ourselves. Let's start with this example right here. Let's work on representing this derivative as a power series. And so to get this into this form of a divided by 1 minus r, what we want to do is somehow have 1 minus some common ratio in the denominator. So what we can do to change this plus to be a negative sign is make x squared negative, right? What we can say is that this is equal to 1 divided by 1 minus negative x squared, right? Because when you subtract a negative value, that's the same as adding it. So 1 minus negative x squared is the same as 1 plus x squared. And so now our derivative is in the form of the sum of a geometric series. We have a constant divided by 1 minus a common ratio. And that common ratio involves x. That's typically what you want to have. All right, and so a is equal to 1 and r is equal to negative x squared. So we can rewrite this derivative as a power series, or more specifically, a geometric power series that will look like this. We'll have the sum from n equals 0 to infinity of a, which is 1, times r to the power of n. So we'll have negative x squared to the power of n. Okay, and so now if we simplify, 1 times anything is just going to be that value, so we can ignore that 1. And then I'm going to rewrite negative x squared to be negative 1 times x squared. And you'll see why I'm going to do that in a second. But let's rewrite this to be the sum from n equals 0 to infinity of negative 1 times x squared to the power of n. And now what we can do is take each of these parts to the power of n. So we'll have negative 1 to the power of n and x squared to the power of n. But remember, when you have a value raised to a power and you're raising that to a power, you can multiply those powers, and so x squared to the power of n will be x to the power of 2 times n, or just 2n. And so this will be equal to the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of 2n. Okay, so if I clean up my work, we now have a power series that represents the derivative of the function that we want to find a power series for. All right, and so what we can do to get the power series for that function is integrate this derivative, right? We can integrate the power series that represents the derivative of this function to get the power series that represents the actual function. Okay, so integrating f prime of x is just going to leave you with f of x, and so integrating 1 divided by 1 plus x squared would give us arctangent of x, and that will be equal to the integral of this power series. But how do we integrate a power series? Well, we need to remember our rules for taking the derivative and the integral of a power series. It's actually not too difficult if we have a power series of this form, which is the general form of a power series. What we can do to find the integral of that power series is add 1 to the exponent of the part with x in it. So if we have a quantity of x minus c, or in our example, we just have x because it's centered at 0, we would add 1 to that exponent for that quantity and then divide by that new exponent. That's just the power rule of integration in action, right? So the integral will be a sub n times x minus c to the power of n plus 1 divided by n plus 1. We add 1 to the exponent and divide by the new exponent. And everything else within that series, which is represented by a sub n, that's just everything that doesn't involve x to the power of n. The rest of that series remains unchanged. A sub n is still a sub n. We do not change that in any way. We just integrate the part that involves x, okay? And then one other thing to note about integrating a power series is that you can't forget to add that constant of integration that's necessary whenever you integrate, right? So typically you would add plus c on the end of whatever you're integrating, but in this case that c only needs to be added one time. It doesn't need to be added to every single term of the series, so I just write that on the outside. We have that constant of integration c plus the integral of the power series, okay? And then just as a review, we're going to need this later in our second example. The derivative of a power series can be found by using the power rule for derivatives. So we multiply the exponent of x minus c down and subtract 1 from that exponent. So we have n, the exponent that we multiply down, times a sub n times x minus c to the power of n minus 1. We subtract 1 from that exponent, okay? And just like when we integrate a sub n, the rest of the series remains unchanged. We do not do anything to the rest of the series. We only differentiate the part that involves x, okay? That's what it means to find a derivative with respect to x or an integral with respect to x. Those processes only affect parts that involve x. Okay, so if we go back to our example, if we want to integrate this power series, we will need to use the power rule for integration on x to the power of 2n, but first don't forget to have that constant of integration c. So we're going to have c plus the sum from n equals 0 to infinity of negative 1 to the power of n. That's going to remain the same. We do not change that part of our series. And then we integrate x to the power of 2n by adding 1 to the exponent and dividing by that new exponent of 2n plus 1. All right, so this right here is the integral of this power series. However, we do want to solve for that value of c. And so what we can do is choose a convenient value of x that will allow us to solve for c. And what I mean by that is if we let x equal 0 for this equation, we'll have arctangent of 0 is equal to c plus this power series. And if this x is equal to 0, we'll have 0 to the power of 2n plus 1, which is just 0, times negative 1 to the power of n, which is still 0, divided by 2n plus 1, which is still 0, and so this whole series just becomes 0 when x equals 0, okay? And arctangent of 0 is equal to 0, and so we have 0 is equal to c. And so by letting x equal 0, we were able to solve for c, and so we know that c is equal to 0. So we don't even need to have that c there, and so we would say that this power series right here is the power series that represents our function f of x, which is arctangent of x. All right, this c is just equal to 0, so we don't even need to include that as part of that power series. Okay, so now that we found that arctangent of x is equal to this power series, and this power series is centered at 0 because we just have x raised to a power. We don't have x plus or minus some constant. We just have x to the power of 2n plus 1. And so now that we have that power series, we just need to determine its interval of convergence. Now this is where things get a little bit interesting. What we're going to do to find the interval of convergence for this power series is find the interval of convergence for our first power series that we found for the derivative. And the reason why we do this is because this power series is a geometric power series, and so we can pretty easily determine the interval of convergence. And the interval of convergence for a power series and its derivative and its integral will all be the same besides the endpoints. We will have to check the endpoints manually, but we can find the interval of convergence for this power series, and that's going to be the same for this series as well. We will just have to check the endpoints. And we do that because the power series that results from integrating or taking the derivative of a geometric power series may not be geometric itself. So it's not as easy to find the interval of convergence for that power series directly. We have to first find it for that original geometric power series and then use the results of that for the power series that represents our actual function. All right, now remember, since this power series is a geometric series, we can determine the interval of convergence by looking at the value of r, right? The geometric series converges when the absolute value of r is less than 1. And if you remember, I erased the work, but the value of r for this geometric power series was negative x squared. So if we take the absolute value of that and set it less than 1, what values of x will make this statement true? What values of x will this power series be convergent for? Well, first of all, these absolute value bars are going to eliminate that negative sign. So we're just going to have the absolute value of x squared is less than 1. And then if we take the square root of both sides, the square root of the absolute value of x squared is just going to be the absolute value of x, and the square root of 1 is just 1. So now we would have the absolute value of x is less than 1, which tells us that when x is between 1 and negative 1, that our series will be a convergent series. All right, so the interval of convergence will be from negative 1 to 1, at least for this power series, and this will be the same for this power series, which is the integral of this one, but we will have to check the endpoints because they could change. Negative 1 or 1 may also be included in the values that make this power series convergent. Okay, and one more thing to note here is that the radius of convergence would be 1. At this step right here, we could determine that. We have the absolute value of x is less than 1. As soon as you see the absolute value of x minus c less than some value, that value is the radius, right? In this case, the power series is centered at 0. So when we have the absolute value of x minus 0, or just the absolute value of x less than some value, that value is the radius. Okay, so we know that the radius is equal to 1, so we can also make a note of that. But now what we want to do is check these endpoints for this power series to see if we should include them or not. And after we do that, we will then have completed this example. We will have the power series that represents our function, we have the radius of convergence, and then we'll have the interval of convergence. So if I clean up my work here, let's start by checking the first endpoint of negative 1. When x equals negative 1, our power series will look like this. We'll have the sum from n equals 0 to infinity of negative 1 to the power of n times negative 1 to the power of 2n plus 1 divided by 2n plus 1. We just replaced x with negative 1. Okay, now to simplify, negative 1 to the power of 2n plus 1, this is actually always going to just be negative 1, right? No matter the value of n, multiplying it by 2 is going to make it even. All right, so if n was odd, an odd number times 2 will make it even, and if n is even, an even number times 2 is also even. So this is always even, and we're always adding 1 to it, which means that this power will always be an odd power, and negative 1 to an odd power is always negative 1. And so this is just equal to the sum from n equals 0 to infinity of negative 1 to the power of n times negative 1 divided by 2n plus 1. But now we have negative 1 to the power of n times negative 1 to the first power, and so we have like bases, and we can add those exponents. So this will be equal to the sum from n equals 0 to infinity of negative 1 to the power of n plus 1 divided by 2n plus 1. Okay, and so now we have simplified our series when x equals negative 1 for this power series, and what we want to do is determine whether this series converges or diverges. If it converges, we will include negative 1 in our interval of convergence. We will change the open bracket to be a closed bracket, but if the series diverges, then we will not include that exponent in the interval of convergence and leave this as an open bracket. Okay, so nothing will change if this series diverges. But we have to check to see if it does diverge or if it converges. And in this case, we have an alternating series because we have negative 1 to the power of n plus 1. That is going to make the terms of this series alternate between being negative and positive. And so what we can use to determine the convergence of this series is the alternating series test. All right, now the alternating series test says that a series converges if it meets two requirements. The first requirement is that the limit as n approaches infinity of the sequence from our series must be equal to 0. And that sequence does not include the part that makes the series alternating. So we're not going to include this negative 1 to the power of n plus 1. Instead, our sequence will be 1 divided by 2n plus 1. So we'll take the limit as n approaches infinity of 1 divided by 2n plus 1. And so is this limit equal to 0? Well, as n approaches infinity, we have 1 divided by 2n plus 1, so this n is going to increase towards infinity, so we have 2 times an increasing value plus 1, so this whole denominator is just getting bigger and bigger as n gets bigger, so we have 1 divided by infinity. And 1 divided by infinity will be equal to 0. So the first requirement for the alternating series test is met. Now the second requirement is that our sequence needs to be decreasing. In other words, a sub n plus 1 needs to be less than or equal to a sub n. The next term of the sequence needs to be less than or equal to the previous term. So in this case, a sub n plus 1 is 1 divided by 2 times n plus 1, right? We just replaced n with n plus 1. And then a sub n is just 1 divided by 2n plus 1. Okay, now we could go through and simplify this denominator, but what's important to realize here is that these numerators are the same, but the denominators are different, and this denominator is always going to be bigger than this denominator, right? We're multiplying 2 by a value that is bigger than this value, right? We have 2 times n plus 1 compared to 2 times n, so this is always going to be bigger, and we're adding 1 to it, so this denominator is just always going to be bigger than this denominator. And when the denominator of a fraction is bigger, the value of that fraction is smaller, all right? So compared to this fraction will have a smaller value for all values of n. So it's true that a sub n plus 1 is less than or equal to a sub n. Our second requirement is met, which means that our series converges, and so when x equals negative 1, the power series is a convergent series, and so negative 1 should be included in the interval of convergence. All right, so we'll erase the open bracket and change it to be a closed bracket, and now we can work on checking the other endpoint, and then we'll be done. All right, so if I clean up my work, when x equals positive 1, that's the other endpoint we need to check, our series will look like this. We'll have the sum from n equals 0 to infinity of negative 1 to the power of n times 1 to the power of 2n plus 1 divided by 2n plus 1. All right, now 1 to the power of 2n plus 1 is just going to be 1, right? 1 to the power of anything that's finite is just going to be 1, and so this is just equal to the sum from n equals 0 to infinity of negative 1 to the power of n times 1, which we don't need to write, divided by 2n plus 1. All right, and so now if you notice, this series that we have right here is almost identical to the series that we just tested for the other endpoint, right? The only difference is that instead of having -1 to the power of n, we had -1 to the power of n plus 1 in the numerator. But that's actually not going to change the convergence of this series. Either way, this is still an alternating series, and so we would just use the alternating series test again for this series, and we would find the same results. The limit as n approaches infinity of 1 divided by 2n plus 1 is still going to be 0, and 1 divided by 2n plus 1 is still a decreasing sequence. And so since this is almost identical to that other series, we can save some time and say that from the alternating series test, this series converges. We basically already tested this series for that other endpoint. And so we don't really need to go through that work again. We already know that this alternating series will converge. All right, so since the series converges when x equals 1, that means that our power series is a convergent series for that value, so we need to include positive 1 in the interval of convergence. So we will remove the open bracket and replace it with a closed bracket, and now we have the interval of convergence for the power series that represents the function arctangent of x. Okay, and so with that, that's it for this example. We have now found the power series to represent arctangent, and we have the radius and interval of convergence for that power series. And so let's look at our second example, which is also our last example, where we will take the derivative of a power series in order to represent a function as a power series. All right, so here's our second example. We want to find a power series for this function, f of x is equal to -4 divided by x plus 3 quantity squared, and we want that power series to be centered at 0, and we want to determine the interval of convergence for that power series. Okay, now in this case, this function sort of looks like the form of the sum of a geometric series, but not quite, right? What we're looking for is some constant divided by 1 minus a common ratio. We have a constant in the numerator, but in the denominator, we have x plus 3 quantity squared. So that doesn't quite match up with the form of the sum of a geometric series. However, if we integrate this function, something interesting will happen, right? If we integrate f of x dx, that will be equal to the integral of -4 divided by x plus 3 squared dx. We could use u substitution to solve this integral. We could set u equal to x plus 3, and then du dx would be equal to 1 because the derivative of x is 1 and the derivative of 3 is 0. And so du is equal to dx if we multiply both sides by dx, which means that this integral would be equal to the integral of -4 divided by u squared times du, right? We replaced x plus 3 with u and dx with du. And if we move u squared to the numerator by making the exponent negative, this would be equal to the integral of -4 times u to the power of -2 du. And now we can use the power rule for integration on this term. We'll add 1 to the exponent and then divide by that new exponent. So this would be equal to -4 times u to the power of -1 divided by -1, right? -2 plus 1 is -1, and then we divide by that new exponent of -1. All right, now you could add that constant of integration plus c, but what we're going to end up doing is rewriting this integral as a power series that we are then going to take the derivative of, and so the derivative of a constant is just 0, so we can just ignore this constant of integration. We don't need that. It's not going to affect our answer. All right, but if we simplify what we have here, these two negatives will cancel out, and we can replace u with what we set it equal to. And so this will be equal to 4 times x plus 3 to the power of -1. But then if we move that quantity to the denominator by making that exponent positive, then we will find that the integral of our function is 4 divided by x plus 3. And that is a function that is similar to the form of the sum of a geometric series, right? A divided by 1 minus r. This is a whole lot closer to this form than the original function is. We can actually manipulate this function into this form where x would be part of that common ratio r. So if I clean up my work here, we can work on rewriting this function, the integral of f of x, as a power series, and then we can use that power series to represent this function as a power series. And I already spoiled this a couple times already, but we're going to end up taking the derivative of that power series. But we're not quite there. We first need to rewrite the integral as a power series, and so we need to work on getting this in the appropriate form. We already have a constant in the numerator, so that checks out. But what we want in the denominator is 1 minus a common ratio r, and that r should include x in some way. Specifically, we're just going to want x because this power series will be centered at 0, so we don't want x plus or minus some constant. We just want 1 minus x in some way. You can have a constant multiple multiplied by x, but you don't want x added or subtracted from any value. Okay, so the first thing I'm going to do is reorder these terms in the denominator and say that this is equal to 4 divided by 3 plus x, because that puts x in the position to be part of that common ratio. And now what we can do is have 3 minus the common ratio by changing this plus to a minus and making x negative, right? So this would be equal to 4 divided by 3 minus negative x. Subtracting a negative value makes that value positive, so 3 minus negative x would be 3 plus x. And now we're closer to having this function in the form of the sum of a geometric series. We have a constant divided by 3 minus a common ratio. The only thing that's not right is that this 3 needs to become 1. And so we can do that pretty easily. What we can do is divide the numerator and denominator by 3. In other words, we can multiply by a form of 1 of 1/3 divided by itself. And so if we do that, we'll have 4/3 in the numerator and then 1 minus negative x divided by 3 in the denominator, right? 1/3 times 4 is 4/3, and then 1/3 times 3 is 1, and 1/3 times the negative x is negative x divided by 3. Okay, and so what we're left with is a function that is in the form of the sum of a geometric series. We have a constant divided by 1 minus some common ratio. And we have x multiplied by a constant multiple of negative 1/3, which is totally fine to have for that common ratio. Okay, so if I clean up my work, remember that the form of a geometric series is the sum from n equals 0 to infinity of a times r to the power of n. So we can rewrite this function as a power series by recognizing that a is equal to 4/3 and r is equal to negative x divided by 3. So we could rewrite this to be the sum from n equals 0 to infinity of a, which is 4/3, times r to the power of n. So we'll have negative x divided by 3 to the power of n. Okay, and so now we have a power series that represents the integral of our function. But before we do anything else, let's simplify this as far as we can. First thing I'm going to do is rewrite this from being negative x divided by 3 to be negative 1 times x divided by 3. So what I mean is that this is equal to the sum from n equals 0 to infinity of 4/3 times negative 1 times x divided by 3 to the power of n. And now we can take each of these parts to that power of n, and that will give us the sum from n equals 0 to infinity of 4/3 times negative 1 to the power of n times x to the power of n divided by 3 to the power of n, right? So we raise negative 1 to that power, x to that power, and 3 to that power. Okay, so if I clean up my work, we can simplify this power series further. Notice that we have 3 and 3 to the power of n in these denominators, so we can actually multiply those together and add their exponents. So we'd have 3 to the power of n plus 1, and so this would be equal to the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times x to the power of n divided by 3 to the power of n plus 1. And now we have a series in its simplest form that represents the integral of our function. Okay, but that's not the power series that we want to find, right? We want to find a power series that represents this function, not its integral, but now we can find it from this power series for the integral. What we can do is remember that the derivative of the integral of a function is just going to be equal to that function. So we can take the derivative of this power series, which represents the integral of that function, and the derivative will be the power series that represents this function. Okay, so since this power series is the integral, if we take the derivative, d dx, of that integral of f of x dx, that will give us f of x, right? The derivative of an integral leaves us with just that function. And so f of x will be equal to the derivative of this power series. And so we can use the power rule for derivatives and multiply the exponent of x down and subtract 1 from that exponent. So the derivative of this power series that will represent this function will be the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times x to the power of n minus 1 divided by 3 to the power of n plus 1. All right, so we multiplied that n down to have n times x to the power of n minus 1. We subtract 1 from that exponent. Okay, and so this right here, this power series represents our function f of x, or negative 4 divided by x plus 3 quantity squared. Now all we have to do is determine the interval of convergence for that power series. And so just like we did with the previous example, we're going to find the interval of convergence from the first power series that we found that represented the integral. And because the interval of convergence for a power series and its derivative will be the same other than the endpoints, we can use that interval of convergence for this power series for its derivative. We will just have to make sure to check the endpoints to see if we should include them or not. Okay, and just as a reminder, we do that because this resulting series from taking the derivative of the geometric power series may not necessarily be a geometric series itself, so it's not as easy to find that interval of convergence like it is for a geometric power series. Okay, so remember that a geometric power series, or just a geometric series in general, converges when the absolute value of the common ratio is less than 1. In this case, the common ratio for that geometric power series was negative x divided by 3. So the absolute value of r is just going to be x divided by 3, right? The absolute value is going to remove that negative. So we're looking at the absolute value of x divided by 3 less than 1. And if I clean up my work here, we want to solve for the values of x that make this statement true. When will the common ratio be less than 1? And so these absolute value bars aren't going to affect this 1/3. So we can pull that to the outside and have 1/3 times the absolute value of x less than 1. All right, 1/3 is already positive, so the absolute value bars wouldn't change that. And now we can multiply both sides by 3 and have the absolute value of x is less than 3, because 1 times 3 is 3. All right, and now we have a statement in the form of the absolute value of x minus c less than some value, which we would call the radius of convergence, right? Since our power series is centered at 0, we would have the absolute value of x minus 0, which is just the absolute value of x. And so since we have that, and it's less than some value, that value is the radius of convergence. And so we would say that the radius of convergence is equal to 3, and so we can make a note of that. And now we can find the interval of convergence, and that will also be the radius of this power series, not just this one. The radius is shared by a power series and its derivative. It's the interval of convergence that might be a little bit different. We might gain some endpoints, all right? And so the absolute value of x less than 3 implies that x is less than 3, but greater than negative 3. When x is between negative 3 and 3, this power series converges. But that might not necessarily be true for this power series, which represents our function, but it's the derivative of this power series. So we need to check those two endpoints to see if they should be included in the interval of convergence. So we're starting out with negative 3 to 3, not including either of those endpoints, but now we need to check each of them individually to see if we should include them. All right, this is the final interval of convergence for this power series, not its derivative, which is the one that actually represents our function. Okay, so if I clean up my work here, let's start by checking the first endpoint when x equals negative 3. So when x equals negative 3, our power series will look like this. We'll have the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times negative 3 to the power of n minus 1 divided by 3 to the power of n plus 1. All right, so we just replaced this x with negative 3. And so to simplify, we can split up this power in the numerator. We can have negative 3 to the power of n and then negative 3 to the power of negative 1. And we can do the same in the denominator here. We'd have 3 to the power of n times 3 to the power of 1. That's going to help us simplify things here a little bit. So this will be equal to the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times the negative 3 to the power of n times the negative 3 to the power of negative 1 divided by 3 to the power of n times 3 to the first power. All right, now we have negative 3 to the power of n in the numerator and 3 to the power of n in the denominator. We can combine those to be one fraction. And so here's what I mean by that. This would be equal to the sum from n equals 0 to infinity of 4 times the negative 1 to the power of n times the negative 3 to the power of negative 1 divided by 3, and we can multiply that by negative 3 divided by 3 raised to the power of n. All right, so I just moved negative 3 to the power of n and 3 to the power of n outside of this fraction. They're still being multiplied by the rest of everything, but now they are their own fraction, and since they were both raised to the power of n, we have both of those values to that power of n. And now, negative 3 divided by 3 is equal to negative 1, and so this is just negative 1 to the power of n, and so this would be equal to the sum from n equals 0 to infinity of 4 times the negative 1 to the power of n times the negative 1 to the power of n, and I'm going to move this negative 3 to the power of negative 1 to the denominator, right? If we move that to the denominator, that power will become positive, and we just have negative 3 in the denominator, so then we will divide by 3 times negative 3. Okay, so negative 3 divided by 3 was a negative 1, so we have negative 1 to the power of n, which is now right here in our expression. Now I need to simplify further, so I will first clean up my work. And now what we can do is combine both of these negative 1s to the power of n. And we can do that by adding their exponents, right? So we'll have negative 1 to the power of n plus n, which would just be negative 1 to the power of 2n. And in a denominator, I'll multiply 3 and negative 3 to have negative 9. So this is equal to the sum from n equals 0 to infinity of 4 times negative 1 to the power of 2n times n divided by negative 9. All right, now negative 1 to the power of 2n, that is always going to be positive 1, right? No matter what value of n we plug in here, whether it's even or odd, an odd number times 2 will be even, and an even number times 2 will be even as well. So we always have negative 1 raised to an even power, which will always result in positive 1, and so this is just positive 1. All right, so we can just remove that and say that it's 1. And so what we're left with will be the sum from n equals 0 to infinity of 4n divided by negative 9. Now, if we move 4 and negative 9 to the outside of the series, we don't need to have them within it. We can just multiply them by that series. Then we would have that this is equal to negative 4/9 times the sum from n equals 0 to infinity of n. All right, so that whole complex series is now just negative 4/9 times the sum from n equals 0 to infinity of n. And we can determine the convergence or divergence of this series pretty quickly. We can use the divergence test for this series, and the divergence test says that if the limit as n approaches infinity of the sequence from your series doesn't equal 0, then your series diverges. So in this case, if we take the limit as n approaches infinity of n, that is our sequence from the series, that limit's just equal to infinity, right? As n approaches infinity, n approaches infinity. And so that is not equal to 0. And so from the divergence test, we can conclude that our series diverges. All right, so when x equals negative 3, the series diverges, which means that negative 3 is not a value of x for which this power series is convergent. So we will not include negative 3 in that interval of convergence. We will leave that open bracket open. All right, and so now what we have to do is check our other endpoint, positive 3, and then once we check that, we will have completed our interval of convergence and this entire example. So if I clean up my work, when x equals positive 3, our series will look like this. We'll have the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times 3 to the power of n minus 1 divided by 3 to the power of n plus 1. All right, so we just replaced this x with positive 3. And now what we can do is simplify a little bit. 3 to the power of n minus 1 can be split up to be 3 to the power of n times 3 to the power of negative 1. And 3 to the power of n plus 1 can also be split up to be 3 to the power of n times 3 to the first power. So this is equal to the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times 3 to the power of n times 3 to the power of negative 1 divided by 3 to the power of n times 3 to the first power. All right, now notice we have 3 to the power of n in the numerator and denominator, and so those are going to cancel out. Anything divided by itself is just 1. And then if we move this 3 to the power of negative 1 to the denominator so that that power is positive, we'll have 3 times 3 in the denominator. And so this will be equal to the sum from n equals 0 to infinity of 4 times negative 1 to the power of n times n divided by 3 times 3. Now 3 times 3 is 9, and then we'd have 4 divided by 9 that we could pull out to the outside of the series. Right, we don't need that constant multiple there. We can just pull it to the outside of the series, and this will be equal to 4/9 times the sum from n equals 0 to infinity of negative 1 to the power of n times n. All right, so now we have fully simplified our series when x equals 3 for this power series, and now we can work on determining if this series converges or diverges. But before we do that, let me clean up my work. What we have here is an alternating series because we have negative 1 to the power of n times n. That negative 1 to the power of n will make the terms of the series alternate between being positive and negative. And so what we can do to determine the convergence or divergence of this series is use the alternating series test. And so the alternating series test says that this series will converge if it meets 2 requirements. Let's check the first one. The first requirement is that the limit as n approaches infinity of the sequence from our series must be equal to 0. And that does not include the part that makes the series alternating. So our sequence will not be negative 1 to the power of n times n, it will just be n. All right, so we're going to have the limit as n approaches infinity of n. But now the limit as n approaches infinity of n is equal to infinity, right? As n approaches infinity, n approaches infinity. But that's not equal to 0, and so the alternating series test fails and tells us that this series is a divergent series. All right, so you could say that from the alternating series test, along with the divergence test, because that's basically what we used here in this first requirement for the alternating series test, since that limit is not equal to 0, we can conclude that this series diverges. Okay, and since it diverges, that means that this power series is not convergent when x equals 3, which means that 3 should not be included in the interval of convergence. All right, so in this case, we did all of that check work just to say that, yep, this is the interval of convergence. We are not including any of those endpoints. All right, so it kind of seemed like a waste of time to do all that checking, but you need to do it anyway because there's always a chance that one of those endpoints could be included for the power series that represents your function when you had to either take the integral or derivative of a power series to get that power series. All right, so always be sure to check your endpoints. Okay, so to close things out, if you see a function that you want to represent with a power series, and you can recognize that its integral is a function that's similar to the sum of a geometric series, then you want to take that integral and represent it as a power series, and then take the derivative to get the power series for your function. Okay, so it might be good for these types of problems to get yourself familiar with what types of functions will have derivatives or integrals that will be in a form similar to the sum of a geometric series. You got to see a couple different types of functions from the examples in this video as well as the lesson video for this topic, but there are others that you might encounter as well. So just keep that in mind as you work through more of these problems. All right, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.